Hello and welcome to Telefunkian. Today we're going to be looking at the calibration of the Roland TR-808 drum machine. Calibration of the 808 involves calibration of three clock signals: the CPU clock, the internal clock, and the tempo clock, as well as four signals that influence the sound of the 808. These include the noise generation, the hand clap, and two frequencies that make up the cowbell sound. In order to properly calibrate the 808, we need to be able to measure the speed of the clock, and that is measured in milliseconds. In order to calibrate the clock signals, you'll need an oscilloscope or a frequency counter, and in order to calibrate the noise generator, you'll need the ability to measure millivolt levels of AC voltage in RMS. Similarly, to measure the hand clap, you'll need the ability to measure AC voltages peak to peak, and I recommend the use of an oscilloscope for this. Cowbell frequencies, again, require either an oscilloscope or the use of a counter. Calibration of the cowbell requires, again, either an oscilloscope or a frequency counter and a calculator. In order to perform the calibration, you'll need to connect your test equipment to various test points on the 808 circuit boards, and you will need to program hand clap patterns and cowbell patterns. So you'll need to understand how to program the 808 in order to calibrate it. If you've come this far without learning how to program your 808, now is a great time to read the operator's manual. The test points and their nominal target readings are listed in the table shown on your screen. In addition, there's a map here of the location of each individual test point and the trim pots that you'll use to make these adjustments. Some of the trim pots are very finicky, very sensitive, and so you may find it difficult to achieve the exact, precise target reading. In addition to manipulating various trim potentiometers, you're also going to need to adjust an adjustable transformer that governs the CPU clock speed. This is located on the component side of the main circuit board for the 808, and this means that you'll need to have the cover off of the 808 and remove the circuit board assembly from the front cover. This is the only adjustment that requires access to the component side of the circuit boards. As the calibration of the 808 involves powering it up while open, I recommend a couple of minor adjustments prior to proceeding. In the first case, I've dismounted the main power switch from the top panel, and I've wrapped it in electrical tape to protect it from shorting out as it rests on the bottom half of the 808 case. In the second case, I've replaced the ground cable that connects the bottom of the 808 with the top panel of the 808 with a longer variant, which allows you a little bit more flexibility as you're moving the top and the bottom half of the instrument around your workbench. I would also recommend that rather than attempting to make these adjustments while holding your oscilloscope probe in one hand, that you actually solder a short piece of wire to each test point and then clip your oscilloscope probe to that wire to allow you to make the adjustments with both hands. In order to adjust the CPU clock speed, you're required to measure a signal present at test point 1, which is a pin on the CPU, the MPD650C085. This microprocessor, IC4, is essentially unobtainable, and it is a CMOS circuit which is prone to failure as a result of damage by electrostatic discharge. As such, I might recommend that rather than touching the microprocessor directly, that you solder a short piece of wire to the transformer that you're adjusting, as I've done in the video that follows. You'll also see in this video that rather than using a digital oscilloscope, I'm analyzing these signals using an analog discovery module and the associated waveform software. The analog discovery module is mounted in a chassis that I've designed and prepared specifically for the analysis of audio signals, and it integrates switching circuitry with the incorporation of a dummy load, internal and external speakers, and allows me to conduct the types of analysis that we'll be performing in today's video. I hope you enjoy this video. You'll see that the calibration of an 808 is both one part science and one part art, and that's part of what makes each 808 sound just ever so slightly different. So before we begin any adjustments, I'll show you my instrumentation setup here. Starting with the function generator, which is this FG502 function generator, which is displaying the reference signal, which is shown in the blue trace on the waveforms software. It's mounted in this Tektronix TM506 chassis, which also houses a DC power supply, a counter, a auto-ranging digital multimeter, and a distortion analyzer, which we might get to later. The software is Waveforms, which is the software for the Digilant Analog Discovery. The analog discovery device is mounted in the second chassis here, the chassis on the top. It's powered by USB and it's connected to the computer through this USB cable. I have mounted it in this chassis with a dedicated power supply, because although the analog discovery can be powered by USB, it's notorious for demanding more power than the average USB outlet likes to provide. So this chassis allows me to connect any audio source to a number of dummy loads, either 4, 8, or 16 ohms, and then analyze the results using the analog discovery module connected to the software, either going through a dummy load, an internal speaker, or an external speaker. Here you can see the reference signal coming from the function generator. It's going into input 2, that's the blue trace on the waveform software, and then input 1 is connected to the 808 over here, and that's the oscilloscope probe connected to pin 1 of the multiprocessor. And then over here we have the analog discovery software waveforms running on a Macintosh Air, which itself is running Windows. So that's the setup, and that allows us to determine that indeed our TR-808 clock is too slow. It's about 424 kilohertz when it should be an even steady 500 kilohertz. So we'll see what we can do about that after we release the circuit board from the chassis and make some adjustments to that transformer. So what I've done is I've soldered a wire to the terminal on the coil of IFT1, the transformer that's attached to pin 1 on the integrated circuit of the microprocessor. We'll be measuring from this pin as we adjust the CPU clock speed. You can see on the oscilloscope that it's already been adjusted. I've been cheating. You can also see I've grounded the board to the power supply board. This is the transformer right here. Ideally, you'd be using a non-metallic adjustment tool. If we turn it counterclockwise, we see the rate increase. If we turn it clockwise, we see the rate decrease. We're going to attempt to bring it back to 500 kilohertz. We're at about 490. Right about there is about 500 kilohertz. We'll take an average of that reading. $499.3 or 4. Now keep in mind, this is with the circuit board out of the chassis. So what happens when we put the circuit board back in the chassis? Does that influence the CPU clock speed? Well, let's find out. So we can see that by reconnecting the circuit board to the chassis, we've reduced the clock speed slightly. We're about 485 or so. Let's see if we can adjust that, make it closer to the target 500 kilohertz. Well, that's a little increase, about 492 or so. It's possible we won't be able to get to the target 500 kilohertz. That looks like it's about as high as it's going to go. $488, that's as high as it'll go. It's a lot better than it was, though. You can see all the jitter in the oscilloscope. That's how unstable the clock speed is. There's our master CPU clock set. That is the only adjustment that requires access to the component side of the circuit board. So we'll turn the instrument off, disconnect the oscilloscope probe. So now we're ready to examine the next calibration point. That's the internal clock. We're looking for a target of 1.9 milliseconds per cycle on test point 2. The probe is connected to the red wire, which has been soldered onto test point 2. You can see a period of 1.85 milliseconds. We'll try to adjust that. We adjust that by adjusting trimmer 1. Watch how sensitive this is. Even just touching it causes a massive increase. Almost doubling it The capacitance associated with touching the trim pot is causing this variation, so we need a non-metallic adjustment tool. You might have one of these if you do have an oscilloscope probe, because very often an oscilloscope probe will come with a non-metallic adjustment tool that is used to adjust the capacitance of the oscilloscope probe itself. And that's what I'm using here. It has a metallic tip, but the shaft itself is non-conductive. And you can see that there's no perturbation of the clock period when I touch the potentiometer using this tool. And that's a very small adjustment. By turning it counterclockwise slightly, it increases substantially. So the challenge here will be to get the target period of 1.9 milliseconds. This trim pot might be a candidate for replacement with a multi-turn trimmer. .92 is closer. Let's see if we can breathe on it and get it down slightly. This one is very finicky. So I think we'll just leave it there at 1.86. That's as good as it's going to get. The next adjustment is measured off of test point 3. And here we're going to be adjusting the tempo clock. With the fine tempo knob fully clockwise, we should see an 8.3 millisecond cycle. So adjust the fine tempo fully clockwise. Tempo is also now fully clockwise. We should see 8.3 milliseconds per cycle, and we're seeing 6.9 milliseconds per cycle. So let's see if we can slow this clock down just a little bit. But before we do that, we move the tempo fully clockwise, and we should see about 62 milliseconds per clock period. And we see about 57. So again, we need to slow the clock down a little bit. So let's bring the master tempo back all the way down. So this adjustment is made on trimmer 2. And it's hiding right here under all these wires. So this trim pot is similarly sensitive, but not anywhere near as sensitive as the first one. Now we decrease the tempo all the way, and we're looking to see about 65 milliseconds, plus or minus 5 milliseconds per cycle, and we're right in that range at 68 milliseconds per cycle. So it looks like our tempo clock is set. So next we're on to test point 4, and we're going to be measuring an AC voltage off of test point 4. We're looking to measure 130 millivolts RMS off test point 4. And let's find test point 4. It's right here in between the microprocessor and the heatsink. In this case, we're looking for 130 millivolts RMS, and we're going to be adjusting this using trimmer 4. Scope says we have about 118 millivolts or so. We'll attempt to adjust that. This is influencing the noise generation circuitry, which is part of the clap sound, the snare. Turning this clockwise decreases the value. So to increase it, we'll turn it counterclockwise, just ever so slightly. Oh, we have a noisy pot. Turning it counterclockwise decreased it even further. So here I'm moving it back and forth quickly a few times to try and clean it. And then bring it back into range, targeting 130 millivolts. About 132 millivolts or so. Resetting the average. Slight overshoot at 135. 134 now. And again, this is where we wish we had installed multi-turn potentiometers. What we've done is we have soldered a multi-turn trim potentiometer to the position here where trimmer 4 was located previously on the other side of the board. Trimmer 4 was one of these style single turn 22K potentiometers, and I wasn't satisfied with the ability to control the noise value as precisely as I wanted to. If you'll recall, this is measured off of test point 4 and adjusted with trimmer 4. So I replaced the single turn trimmer with this Bourne's multi-turn pot. It's mounted on the opposite side of the board, on the foil side, so-called foil side, although this is a double-sided board. This is relatively straightforward to do. Just soldered it onto this side of the board, and I had to bend the center pin on the multi-turn so that it would actually fit in through the holes. So this works out quite well. The resistance was set to a middle value to about 25 kilo ohms. This is a 50K potentiometer. This potentiometer is acting as a variable resistor measuring between the central wiper and one of the arms of the pot, as opposed to an arrangement where the residual signal is shunted to ground, for example. So you can see that if we turn on the input, we're measuring the magnitude of the noise signal in yellow here, and we're looking at AC RMS, and the value is approximately 133 millivolts. The target value is 130 millivolts, and this is AC RMS. As it is a noise signal with a certain degree of randomness, you can see that some of the spikes are over 400 millivolts, so 800 millivolts peak to peak. So right now, as I'm adjusting this, we're getting about 128 or so millivolts. I can make very precise adjustments, turning it up to 139 millivolts or bringing it down, but turning it clockwise with a much greater degree of precision than I would have had with the single turn potentiometer. So we have lots of room to maneuver and get exactly the value that we're looking for. And this is important because this is what the machine was designed for, 130 millivolt noise signal, and this influences the clap sound, the toms, and the snare. So we want this noise signal to be as close to the value that the instrument was designed for as possible. If we reset waveforms, we see the average is almost exactly 130. Again, some of the values are almost 800 millivolts peak to peak, but again, the ACR mass is 130. So we have a pattern running with a clap in the pattern. We'll let you hear that. And we'll examine that and adjust the clap offset. This is the signal off test point 5. which we monitor to adjust the clap offset. It's adjusted using trimmer 3. It's approximately where we want it to be. Maybe we're slightly low. In this case, we're looking for the peak-to-peak value at what's labeled the output, which gives us the blue trace, as opposed to the ACRMS value. And we're looking specifically at the third signal, the third portion of the clap. There are 3 envelopes that comprise the clap sound, 2 shorter, lower amplitude envelopes, and then 1 larger and longer envelope. And we're looking for 6 volts peak to peak. And as it has a heavy noise component, there's a certain degree of randomness there. If we increase this above 6 volts peak to peak, we end up with not only a louder clap, but one that has a longer duration and contains more of what sounds like reverb. It's not reverb per se, but you can see that's what it looks like if we turn it up. And it sounds a bit different. As we end up with more of this reverb sound, that's probably not desirable, because ideally, if that's what you're looking for, you could add that in the studio using outboard processors, or if you're using a DAW and mixing in the box, you can of course use plugins and the like to get that type of effect. So we're adjusting this to 6 volts peak to peak. It's a bit twitchy. It could perhaps do with a multi-turn as well. However, we'll make do here with a single turn potentiometer. And just very fine adjustments, looking at the average value and resetting that averaging, which is helpful when trying to assess noise containing signals. So that's about right, 5.8-ish. Oh, too low. Closer at 6.07 now. This is pretty close. We have an average just a little below 6, which is fine. So I think we're done with that adjustment. Again, the multi-turn potentiometer replacement can be accomplished quite easily. It's not necessary, but it does make adjustments more straightforward. These are Born's potentiometers ordered from Mauser. In the case of the noise potentiometer, we're using a 50K instead of the 22, which gives us the ability to reduce the gain a little bit in the noise circuitry. These potentiometers have a 2.54 millimeter pitch and a slightly different configuration, whereas the original single-turn potentiometer has something resembling a more equilateral arrangement. And so you need to bend the center pin in order to facilitate placement in the holes pre-drilled in the board, but it's relatively straightforward. So you can see the difference in the pin configuration here. Of course, because these potentiometers only offer adjustment from the top, you have to place them on the foil side of the board so that you can actually make these adjustments while you're monitoring the test points. So I hope that's interesting and informative and helpful for those of you who are having challenges adjusting your 808. This is another example of the benefits of using a multi-turn trim potentiometer in place of a single turn. And this is trimmer 1, which we use to adjust the internal clock. It's supposed to be 1.9 milliseconds per cycle. And it was very difficult, very twitchy with a single turn pot. And we've replaced that with a multi-turn trim pot. And it's very straightforward. We have a lot of control, a lot of precision, and here you can see that we're just making very small adjustments in going from 1.91 milliseconds to about 1.9 milliseconds per cycle. So we couldn't really imagine any more control than this, and so this is something that you can do if you need to get control over the calibration of your 808, is replace some of these more twitchy potentiometers with multi-turns. Next, we're looking at the cowbell. And now we're set up to measure the cowbell frequencies. First, we have a scope connected to test point 6. We should be measuring 1.8 milliseconds per cycle. And right now it looks like 1.75. We'll see if that adjusts. And indeed it does. And it's considerably more straightforward making these adjustments than the others that we've done previously. So turning it counterclockwise increases the value. So 1.849 is very close to 1.85. So the next cowbell frequency, this is adjusted by adjusting trimmer 2. Again, these are on the so-called voice board rather than the main board, which is why they have the same designations as trimmer 1 and trimmer 2 on the main board. We're on test point 7 and looking for 1.2 milliseconds per cycle. And we have 1.22 milliseconds per cycle. So let's see how sensitive this one is. And you'll absolutely notice the difference in sound if your cowbell frequencies are off. .2495, very close to 1.25. So very close to the target, and these are the adjustments right out of the service manual. You can see here all the test points are mapped out. If you can't find them, there's a map of all the test points in the service manual, and you can pause the video here and take a screen capture. That's all for today's video. I hope you enjoyed it. If you did, please give it a thumbs up, subscribe, and consider leaving a comment. I hope to see you again soon.